Hello, and welcome to another episode of the Gradient Podcast. We interview various people who research, build, use, or think about AI, including academics, engineers, artists, entrepreneurs, and more. I am your host, Daniel Bashir, and in this episode, I am very excited to be interviewing Professor Sebastian Raschka. Sebastian is an assistant professor of statistics at the University of Wisconsin-Madison and lead AI educator at Lightning AI. He has written two best-selling books, Python Machine Learning and Machine Learning with PyTorch and Scikit-Learn. Sebastian is a truly incredible educator, and if you have seen any of the wealth of educational content he has put out online, you're probably well aware of his talents and his ability to really bring together high level conceptual information with low level mathematical details. This was a great opportunity to learn from him, not only the way he approaches being an educator, but also a learner. I hope you enjoyed this conversation as much as I did. I'd love to hear a little bit about how you yourself became interested in AI. I and many other people are pretty familiar with your AI education work, and I think that you do an incredible job of explaining concepts and ideas. And so I'd love to hear your path to how you got interested in AI in the first place, and then how you kind of got to where you are.
Yeah, so that is an interesting question. So my journey goes way back, a little bit more than 4 years, a little bit older than the gradient, although I regularly read articles on the gradient. So it's something I maybe at least every 2 weeks send to my ebook reader and read. So there's usually something interesting. So yeah, where I got into AI, that must have been like 2010, 12-ish. I took a class back in grad school on statistical pattern recognition. And I took that class because I was working in computational biology, and we have a lot of, let's say, interesting data sets. And it would have been interesting, so that was my goal, to learn about how to automate like decision making. Like you have certain data sets, you want to predict something, which is why I took this class. It was very heavily based on Bayesian methods. I think it was like, of course, starting with Bayes classifiers, naive Bayes classifiers, and then Bayesian networks. And from there, I think it was also when the Coursera class by Andrew Ng was launched. Coursera itself was launched like 2012-ish. So I took that shortly afterwards, after completing that class. It was kind of like complementary because the class I took in grad school was more focused on Bayesian methods, and Andrew Ng's class was everything but Bayesian methods. And it gave me really the taste of like what machine learning is like from logistic regression to SVMs and neural networks. And ensemble methods, I think. It's been 10 years, but I think that was like what it covered back then. And yeah, from there on, I was just applying these methods and reading more, getting into deep learning. I started using Theano back then, made the journey to TensorFlow, now using PyTorch. So I learned all of these, let's say, conceptual things from classes, but then really I learned a lot by doing things like working on small projects and applying these methods in my work, working with various data sets. Also like taking a data mining class, which was, I would say, also very worthwhile, learning about frequent pattern mining and so forth. And these types of algorithms. So I think I got like the broad introduction to all these topics in the beginning, but then really try to be more hands-on and learning while doing, which personally was my preferred journey because I like doing things. I would say I'm not like the most patient person, and diving into theoretical things, coming up with proofs. I do this occasionally, but this is not something I do every day. I'm more like coming from the tinkering side, I would say. Yeah.
That makes a lot of sense. Yeah, I think that the sentiment you're expressing seems to have been reflected in a lot of the deep learning educational content we see these days. So, like Fast.ai, for example, very much this top down approach. I think that from my experience, your educational materials as well do a really good job of trying to combine that top down with you give very good insights into what is also going on with the mathematics. So, for example, I think that you had a section on like the transformer architecture in your online deep learning class, which I thought did a really good job of explaining what is going on mathematically here, along with, here's some of the implementations, the high level architectural details. And so you mentioned kind of your hands-on process, but could you maybe dive a little bit deeper into what your process is for picking up some of these new deep learning concepts? There's so much to keep up with, right? And I think that a lot of people sometimes struggle with that. How do I actually effectively learn things in this space? So I'd love to know a little bit more about how you do it.
Yeah, this is like a very interesting and challenging thing, keeping up with what's currently happening. And I think, over the years, I learned to be more selective. I think it comes with time that in the beginning, you want to know it all. You want to learn everything. And because it's just interesting and everything seems exciting. But then at some point you realize, okay, the day only has 24 hours. I have to prioritize here. And I also have to get work done. So I can't just, read things the whole day. So I also, it's as a context, I should mention, I was a moderator for Archive, the machine learning category, CSLG for Archive. And what we did there is we were looking over all the publications each day to just make sure the category is correct and so forth. Sometimes we would check certain articles if they looked like suspicious or there's something wrong or the title was somehow weird. We would check the PDF and make sure everything looks okay. But there you get exposed to so many articles. So it ranges between, let's say, at least 100 new articles to up to 200 to 300, depending on whether there's a conference coming up soon. And then you realize, okay, there's way more interesting stuff than you can keep up with. And this is just archive research articles. There are so many interesting blog posts and videos too. So my approach right now really is I have a notebook on my computer where I have a page for each topic. One could be computer vision with convolutional networks. One is computer vision with transformers. One is natural language transformers and so forth. So I have, or even general things about deep learning, evaluation metrics, interpretability and so forth. I have, let's say 40, 50 sub pages there. And I just keep collecting at that point because there's only so much, let's say, you can read. I usually keep collecting, and then each week I pick out 2 to 3 articles that I read. They could be, randomly, but I usually just scan through this. Oh, this was an interesting one. And this bookmarking strategy, I feel like this helps you keep focused because often you bookmark things that look interesting, but then in the grand scheme of things, there are way more interesting things you could read that you already have on your list. So it's, in that case, you're kind of preventing that you have this fear of missing out because you keep track of everything. But then also it helps me with not getting distracted by the article of the day, that I really just read those that I feel like are most interesting or most important. And at the same time, what helps me then also really learning about a topic is choosing a sub area, something I'm really interested in at that time. So for example, a few months ago, I was really interested in revisiting the topic of confidence intervals. So I read all the methods I had bookmarked and also just compiling things and writing up some code examples, really revisiting a topic deeply. And when I do that, I usually start with a big picture concept, just revisiting what's the problem here, what are we trying to solve, and then really just making even figures for myself. Confidence intervals is maybe not the best examples. There is not that much interesting in terms of what you can do with figures. But let's say, coming back to what you mentioned with the transformers, I would sketch out things and then come up with some code examples for myself. So in this lecture, the lecture was actually a dry run for a book chapter for my new book that came later. So in the lecture, I don't think I had many hands-on code examples. This was more based on the illustrations. And then later, refining that, adding code examples was really making it, I would say, more whole, the explanation, making it more, I would say, comprehensive, but also having both concepts and code examples. And while coding up these examples, I feel like these are multiple layers of how you understand a topic. You start with reading, you compile resources, you read, then you try to make sketches, and then you realize, okay, I'm missing this certain point. So you would go back to an earlier article and think about it again and so forth. And then when you do the code examples, it's yet another more, let's say, detailed level of understanding, because the sketching gives you an understanding or tries to reinforce the understanding of the big concept to see if you understand everything and if you can put or summarize it in a visual way. And then coding it up, you need more detail. You need to know the exact dimensions of the inputs and these types of things. I feel like these all go together where you build your own, let's say, learning path in a way. It's kind of like when you think back of college, it's almost like designing your own homework assignments, that you go from summarize this and then apply this, implement this, right? So in that case, that's usually how I learn, but it depends also on the topic. Not every, let's say, topic requires a code example. Again, it comes back to prioritization that, yeah, I mean, it's probably not feasible to implement everything. And if you learn about, let's say, maybe SVMs or something like kernel SVMs, maybe there it's like it would take too much time to implement that. You can use Scikit-Learn in practice. However, it might make sense to implement a linear SVM or something just for the sake of understanding how an SVM works. So it's like, again, coming back to prioritization, but that's in a nutshell how I do things.
Yeah, that's a really good way of putting it. I like how you thought about or pointed out that there's different levels of abstraction of understanding these things. There's a high level concept. You can dig a little bit deeper into some of the mathematical underpinnings. I kind of understand what the task is, how it's formally represented, what the loss functions look like. And then as you dig deeper, as you pointed out, there's the actual coding of it. In a lot of cases, you are worrying about some very small things. I might start having off by one errors. And so you kind of hop between these different levels. One thing I kind of wanted to tease out from what you just said there is you mentioned it might not be necessary to dive all the way to the bottom in terms of really getting hands on and coding something up. And so I wonder if you think about or change your approach to learning a concept, depending on, I guess, the purpose that you are learning it for. And I can imagine, these might look like aiding in your own research versus it's a topic you want to teach someone else versus, I just came across a set of papers that I want to read for fun because I find that cool. So I'm curious if your approach changes between those.
Oh, absolutely, absolutely. If it's, let's say, for a research project, if I'm trying to develop something new, I'm trying to understand as best as I can related approaches, for example, just to make sure I'm not duplicating any efforts, but also to make sure I really know what I'm doing here, compared to just maybe keeping up. So I must honestly say I'm currently not working on a new transformer architecture, a new architecture for, let's say, natural language processing with transformers. I'm more like using transformers. So in that sense, yeah, I'm trying to implement them, but let's say I don't worry so much about efficiency and how I distribute the training myself, like how to code up all these details. That is something libraries can take care of at that point. I'm more interested in, let's say, the big picture understanding, where I try more like to come up with a rudimentary or simplistic implementation. And for some applications, or let's say computer vision transformers, those I have not implemented myself yet. The reason is, well, I get a good idea of how they work. I looked at conceptual pictures or drawings, and I know how transformers work. And well, it is in a sense, there are some tricks here and there, but in a sense, it's the same idea. And I would say it would take me some extra time to implement them. And yeah, at this point, it's not on my priority list. So I have like a priority list. I wish I had more time and I could implement everything, but well, if I don't really design a new architecture, I can use a library. I don't have to implement it myself if I, let's say, understand how it works. So in that sense, it depends. You have to prioritize. Is it really? You don't have to. Also, that's, I think, an important thing. You don't have to understand everything in detail. It's good to know what's out there. So in case you need it, then you can dive. So it exists, and then you can dive in. But as long, let's say, as you don't actively use it, well, you don't have to, let's say, understand everything, because I think this would be very stressful. It's machine learning is such a big field. You would be infinitely busy just catching up with what other people are doing versus doing something yourself.
Yeah, you could definitely spend your time 24/7 just keeping up with what the latest and greatest is, and I think even some subfields of ML. But I really like that heuristic for considering what is useful and worth my time to learn and to learn deeply, and then prioritizing where to dive deep. Because as you pointed out, you've got your set of priorities, and that is based off of what you were doing at the time. I am conducting this research project, I am writing this book, developing this educational content. And so that is going to almost naturally impose a set of priorities, right, on the sorts of topics that are going to be most beneficial. And then that in turn drives, okay, how deeply do I need to engage with this set of things? If I'm trying to teach somebody else how a transformer works as deeply as possible, then maybe diving into the implementational details is helpful there. But as you said, if I'm conducting a research project where I'm more focused on an application of VITs of transformers to some problem of interest, then maybe I don't need to worry about all the low level details. I think that's a really good heuristic, and it's kind of a nice thing to sort of formalize and articulate. So now that we're on the topic of your research and priorities, I'd love to talk about a couple of the things you've worked on. Let's start with this topic of ordinal regression, which I think you've published a couple of papers on by this point. Could you give just a quick introduction to what that is?
Yeah, so that's a smooth transition from learning to doing. So so here in the ordinal regression setting, what we have is, let's say, think about classification, but with labels that have a natural order. So an example would be Amazon customer ratings, where you have 1 to 5 stars. So you can use a classification algorithm for that to classify, let's say, customer satisfaction based on the number of stars. Or the same thing is true for, let's say, insurance companies having a scale for assessing damage of buildings. So like severe damage, moderate damage, no damage, and things like that. Or for diseases like no disease, moderate, severe, very severe, where you have something where you can classify things, but you have more information than just classification. So in this case, there is a class of methods in classical statistics called Ordinal Regression. And this sits between regular regression and classification. So in regular regression, the difference is that we have a numeric, we have basically, you can think of it in a programming context as floats or as real numbers that you want to predict. So let's say I want to predict the height of a person. It's in centimeters or inches or feet, depending on which country you are in. And I can say, for example, the difference between 100 and 150 centimeters is something I can quantify. It's like a 50 centimeter difference. And then from 150 to 200 centimeters. So I can really quantify things here. Whereas, for example, in ordinal regression, I have usually problems where I have a difference that is not quantifiable. It's like an arbitrary distance. So, for example, coming back to the star ratings on Amazon, I can say, okay, the difference between 1 and 3 stars is 2 stars, and I can compare that to 3 to 5 stars, which is also the difference between 3 and 5 is also 2. However, it's kind of like more subtle than that, I would say. It's really hard to compare. Can't really say the difference between 1 and 3 is the same as 3 and 5. Maybe in this case, you can maybe wing it and also still use a regular regression, but there are other problems like, let's say, the damage to the building. I mean, some people rate the building, let's say, as severely damaged, another building as moderately damaged. But what is the difference? Is it like 3 more shattered windows, or is it more like, I don't know, like the stone is loose or the building is crumbling? It's kind of like an arbitrary distance where it's hard to quantify. Or think about, let's say, rating movies. I have a movie I hate, a movie that is okay, and a movie I really like. But I can't really tell you, I don't know, this movie is 2.2 better than the other movie. It's more like an arbitrary distance between the two movies. And
yeah, there's a subjective quality.
Yeah, right. That's a good point. Where if you have a data set, it should be consistently subjective. So if you have moderate disease, it should be somewhat comparable. But on the other hand, it's really, it would be hard to put a number on it. What is the difference between moderate and severe disease? It's more subjective in a way. And in this case, there are many real-world examples where we have such information where we can't really put an exact number on it. It's really like, okay, there's a difference. You can also think of ranking things, like one is more than the other, but I don't know how much more. even for search results. If you type in a search result, one result is more relevant than the other, but it's like, okay, how much more relevant? There are companies who develop metrics around it, but in a way, it's still kind of like hard to put a number on it, right? So in this case, this is just like a whole set of problems where ordinal regression is really useful. It's essentially classification with ordering information. And I can tell you more of how or what we do there, because I mentioned in the beginning that it's a classic statistics problem. But we basically try to make it work better for deep neural networks. So the focus here was really how can we take an existing deep neural network, let it be VGG, ResNet, could also be a vision transformer. Basically, how can we take an existing neural network, could also be an RNN, anything, and with very few lines of changes in terms of the code, how can we really turn this into an ordinal regression model? Because, if you have a problem and you can use, or you are using a classifier, and I tell you, why don't you consider an ordinal regression model? You don't want to just try a completely different model or develop a special purpose architecture. Really, you want to just ideally change the loss function, similarly how you would change an activation function, and turn this classification model into a regression model. It's essentially a hyperparameter almost. So how do you make this choice a hyperparameter that you can just try out and see if it works? Maybe it works, maybe not. It doesn't cost you much. It's just as simple as it can be to change the setting, basically.
Yeah, I've got a couple of follow-on questions based off of your initial description there, but let's start with this one. Can you just give us a high-level conceptual overview of what exactly is the process whereby I take my pre-trained deep neural network, VGG, VIT, and transform it into this ordinal regression model?
Yeah, so our methods that we developed, they go back to something called a binary extension framework. So this essentially means if you think about a multi-class classification problem, let's say we have these 5 ratings, 1 to 5, where 1 is mild and 5 is most severe. So I want to predict that, something from, or let's say no, mild, moderate, severe, very severe. I have 5 outputs. And instead of having this as a classification problem where I have labels from, let's say, 0 to 4 or 1 to 5, what I do is I make this change that I consider each output node in the output layer of the network. Instead of using a softmax function here, I would just use a sigmoid function where but in addition to that, you turn each output node into a binary classification problem. So you say essentially the first output node is you're saying, is this rating greater than rating 0? The second node is this rating greater than 1? You're asking binary questions. So you're turning this multi-class classification problem into a multiple binary classification problems. And based on that, so the only difference you have to do is you have to convert the input label. Let's say the input label is 5. You convert this into 501 integers. This is actually in the code I have automatically handled. You don't even have to worry about this. So the only thing you do is you change. If you use PyTorch, you don't even include usually the softmax in the output layer. The only thing you really change is the loss function. So in this loss function, you have multiple binary classifiers essentially in the output nodes, and this is essentially it. So you're asking the question: is this greater than 0? Is this greater than 1? Is this greater than 2? And so forth. And if the answer is yes, if you say it's greater than 0, it's greater than 1, and it's greater than 2, it's not greater than 3, the prediction would be rating 3. So you're just looking at the answers, the number of yeses and nos, essentially. And this is essentially it. So this is how you can turn a classification network into an ordinal regression framework using this binary extension framework. And there are multiple ways for designing the loss function then, which is kind of what we focused on. But in a nutshell, it's essentially one approach, maybe the easiest approach, is really this binary extension framework.
This reminds me a little bit of like a one-hot encoding representation, although of course in some cases you'll definitely have multiple ones. One question I have here, maybe on the more applied side of this, is you mentioned that this is a pretty generic method, so I can take pretty much any pre-trained neural network and graft it onto this ordinal regression problem. So if I start with a different pre-trained network, did you find that the specific network, the task that it might have been pre-trained on, did that carry any weight in terms of the performance that it got in ordinal regression tasks downstream, or the types of ordinal regression tasks you were able to apply it to?
So if I may take a step back. So you mentioned it's similar to a one-hot encoding with multiple ones. Yeah, it is more like a multi-hot encoding where you have multiple ones, except the only case where you would have a one-hot encoding is if the first rating would be a 1. Because you have, so in this, I'm saying this because this was the trick. You wanted to make this consistent. So you want these outputs to be consistent. Essentially, when you say it's greater than 1, it's greater than 2, it's greater than 4, then it should also be greater than 3. Because so you can't have like these kind of contradictions. I mean, you can have these contradictions, and then what a previous method had. So internally in our company, we call that the skateboard method, where you develop something and you make it work. It's your first, let's say, approach, and it works great. But then over time, you improve it. So the first network, it was not by us, but the first network, the authors, if I recall it correctly, they were the last name of the first author was NIU. So let's say New and colleagues developed this network that worked incredibly well for ordinal regression, but it has this inconsistency. And we focused on developing different methods to make it consistent. So we have like these multiple ones. And then maybe getting back to the question of the pre-trained networks, I also wanted to clarify. So in this case, actually, we trained the networks from scratch because these were relatively, I would say, different data sets. And they were also relatively small, so it was feasible to train it from scratch. But nothing prevents you from, let's say, pre-training the network or using a pre-trained network on, let's say, ImageNet, and then just changing the output layer. And in fact, people who adopted our methods in practice, they did actually that. So they used some of them. We have the methods so I have a GitHub repository with links to the pre-trained models. Some people used the pre-trained models and fine-tune them to something else. But you can also, like you said, you can just use from Torch Vision Hub or something. You can use any model pre-trained on ImageNet, and you can just change the output layer and use the loss function that we provide, and that's it. You can really use a pre-trained network. You don't have to redesign the architecture, for example. You don't have to. You can train your network from scratch, but whatever your heart desires, essentially. So in that case, I can't specifically say how important the pre-training task is. I would say there is no reason to believe it is different than compared to other classification networks. So I remember there was this paper, it was like a couple of months ago. They looked at self-supervised learning, though, but they found, when I remember correctly, that the more similar data set was to the target data set, even though they used self-supervised learning, which is different, let's say, from the target classification task. The more similar the data set was, the more, let's say, benefit you got out of the pre-trained network. And I think the same is true here too. So if you have a data set that is, for example, a popular benchmark data set for that is age classification. So my reasoning would be, if you care about age classification, pre-training the network on different age data sets or a combined age data set would give you a better performance than, let's say, pre-training a network on ImageNet and then fine-tuning it on age prediction. But that's a hypothesis. I'm pretty confident this should hold. But yeah, I've not done these experiments myself.
That makes a lot of intuitive sense. And yeah, maybe some listener will follow up and see how that works. Before we move on to your work on semi-adversarial networks, I know is a follow-up to your original paper on this rank consistent framework. And in this, you did ordinal regression, but had this additional consideration of conditional training data sets. Can you give me just a quick overview of what was going on in that paper?
Yeah, so good question. So I mentioned briefly the limitation of this rank inconsistency of the original method, which was, I think, 2016 in CVPR. That was not our method. Our method was basically a follow-up to see if we can take an already great method and make it even better, where we proposed this rank consistency to fix the rank inconsistency. And here what we did is we had a weight sharing constraint on the output layer, which means it was a kind of like a workaround. We had like a mathematical proof for that, why that results in rank consistency. But having a weight sharing constraint, which means all the weights in the output layer are different besides the bias units, that means it kind of reduces the capacity of the network. It makes it, let's say, a little bit constrained. In hindsight, we found this was maybe not necessarily always a bad thing, because first it performs better than the rank inconsistent method, but also it overfits less. There's less overfitting, and that's probably because of this restriction. It's kind of like a regularizing effect almost. However, for certain tasks, a reduced capacity means, you're maybe not getting the full performance out of your neural network architecture, because, well, you have this very powerful feature extractor, but then in the output layer, you have this very simple method. It's even simpler than, let's say, a linear model like a softmax regression, because you have weight sharing. You only have the same weight for all the tasks, except the bias units. So what we try to do is we try to think about a different way we can solve this rank inconsistency issue by not having a weight sharing constraint. And what we did here is we had a method where we compute conditional probabilities at each output node. So the conditional probability would be, let's say, if we think about the second node, it's like, what's the probability that the input data point has a rating greater than 2, given that the rating is already greater than 1 based on the first node. So it's in a sense like taking this condition into account, and then if you have these conditional probabilities for each output node, you can use the chain rule for probabilities, or other people call it the general product rule in statistics, where you can just multiply these conditional probabilities to get an unconditional probability. So the probability that the rating exceeds a certain rank. And so here, in order to compute these conditional probabilities correctly, we used conditional training subsets, where you have to have, let's say, reduced training sets depending on what task you train. If you train greater than, if you train the task for, is this rating greater than 3? So you basically reduce, based on the condition that it has to be greater than 2, you reduce the size of the training set. So all the ones where you say it's not greater than 2, you remove them from the training subsets for that given node, essentially. So there's some, let's say, more involved code. The code is more involved for that. You have some, I would say, relatively ugly for loops in Python when you create these training subsets for training the neural network. But on the other hand, you train it on certain nodes on less data, which in that sense, in consequence, it doesn't make the training much slower. And also, it doesn't really affect the performance. On the contrary, like the predictive performance, on the contrary, it performs actually better than the other two methods. So this kind of trick makes the nodes, the outputs, rank consistent. And you have a slightly more expensive loss function because of the selection of the training subsets. But then, since some of them are subsets, training set is smaller, you also gain kind of predictive performance. So it's kind of like, I feel like almost balancing each other out. Oh, I maybe should also say the reason why it's now rank consistent is if you think about conditional probabilities, a probability is a value between 0 and 1. And if you multiply to numbers between 0 and 1, it can't exceed 1, the original value, right? So if you have the original value of 1, you multiply it by 0.9, you can't have something that is greater than the original value. It will be 0.9. So in that case, they have to be ordered. The output nodes have to be ordered because you have this condition on the previous output node. You can't really have an outlier where you have a probability that is higher than the previous node where you get this rank inconsistency. So in that case, it's a very, I would say, intuitive way of solving the rank inconsistency without any fancy workaround, essentially.
Yeah, I really like the intuitiveness of this method. It's kind of neat how you're able to impose this structure whereby we have a pretty natural probabilistic interpretation by virtue of, okay, I've restricted the data set, so automatically I have this condition of, I know that my value, my rank is greater than a certain point, and then I kind of have the prediction problem on top of that. That's really neat. So the other part of your research I was hoping we could discuss was this other thing you've worked on, semi-adversarial networks. Could you give me a quick overview of what these are?
Yeah, it's a very interesting history behind it. I think, I must say, I don't want to claim anything, but I think we had this idea a very long time ago. It was, let's say, the same time around GANs were developed, but I would say it's slightly different. It is, in a way, almost like I would say it as see it as a constraint optimization approach using deep neural networks. So I'm not the, let's say, most sophisticated mathematician working on, let's say, constraint optimization methods. However, this was like really a workaround using deep neural networks to solve complicated constraint optimization, nonlinear constraint optimization problems. So the big picture idea is you have something you want to and this goes back to 2016, I think, when we had our first paper on that. Maybe it was published 1 year later or something. It's not a new idea that we worked on it for several years. So the idea was essentially you have, and I had this originally planned for like a computational biology project where we had, let's say, bioactivity scores, and we wanted to optimize the bioactivity score of a certain molecule. Given that we make certain changes to the molecule, minimal changes. Because if you think about chemistry context, usually in drug discovery, we want to find some molecule that has a certain property, let's say bioactivity, or let's say it should target a certain protein to inhibit a certain disease and so forth. And usually then you try to optimize these molecules, maybe let's say make them less toxic or make them more potent or something like that. So you don't want to really change the overall structure of that molecule. You want to make a minimal change, but you want to maximize the desired outcome. So it's kind of like this kind of like constraint optimization problem in that sense. And it was a little bit complicated. It was slightly before graph neural networks were a big thing. So yeah, I mean, we tried that a little bit, but it was back then beyond, let's say, my capacity to implement all of that in a graph neural network context with the data we had. So I had a colleague, Vahid Miralili, who worked in biometrics, and they had a very similar problem. So they wanted to hide specific information from face images while still having these face images being usable. So for example, in this context, it was gender. So it was network, or they had a previous approach, and we wanted to, let's say, use neural networks to get better results, where we adopted this idea of the semi-adversarial network I had before for the computational biology context. So here, what we tried to do was like removing the gender information from the face images so that no, let's say, company who is involved in data mining could just, let's say, run an algorithm over images and then extract the data out of it without having consent of the people whose face is in the image. So basically making the images more private. However, at the same time, you wanted still the face images to be visible. So there are applications that's maybe not the typical application, but let's think about a passport scanner at the airport, where you still should be able to match two faces. Like if someone scans the passport, it should match the face on the video camera. But at the same time, there should not be more information than that. No person should be able to extract, let's say, personal information like health information, gender information, and these types of things. So in that case, it was a problem that we wanted to optimize the hiding of information while still making minimal changes to the input image. And how we did that was essentially having a classifier. You can think of it as similar to a GAN. In a GAN, you have a discriminator. Here we have a classifier that outputs our, let's say, target function. For instance, let's say a gender classification. And here you wanted to have maximum entropy, that there is no label. I mean, it's like evenly distributed, the output. If you have, let's say, a binary classifier for something, this would be 50-50 essentially. So similar to a discriminator in a GAN. And the other network was an autoencoder where you minimize the changes from input to output. So you make minimal changes. And in the face recognition example, we had a third component, which was a face recognition classifier, which is kind of having a similar function as the autoencoder. So, and this was so that you don't accidentally generate adversarial networks. Sort of like real adversarial examples where you make 1 or 2 pixel changes, but also destroy the whole face matching essentially. So yeah, in a sense, you can think of it broadly as a way to optimize certain things with neural networks. And for example, you can apply that. That is something I worked on. I'm not working on it currently anymore because I have too many projects. But if someone wants to work on it, for example, for directed evolution, if you think about optimizing a protein, let's say a sequence, you have a sequence of a protein, you use a transformer network. How do we make minimal changes to the sequence so that the protein is still intact while maximizing a certain score that you have, like a bioactivity score or something like that?
Yeah, I like that this is a really general framework. So it seems like there's kind of this three-part process we've got going on here, right? I am generating a perturbation of an original source of data. So maybe I have an image, maybe I have a protein sequence. And then on top of that, there's these two additional things of one, maybe I'd like to confound something. So as you said, I'd like to maybe remove information about gender that a classifier could pick up on. But then this additional part, so as to make sure it's not actually adversarial, I have to include this other component of let's actually preserve the overall integrity so that I still recognize like this picture of Daniel's face is still Daniel's face. This picture of Sebastian's face is still Sebastian's face, and so on. So it sounds like a very general kind of framework that can be applied in lots of places.
And if I may interject, and you perfectly described why we named it semi-adversarial, because one aspect is adversarial. You are, let's say, confounding, in this case, the gender information. The other part is not adversarial because you leave it intact, like the face recognition intact. So in this case, yeah, it's half or semi-adversarial, essentially.
Yeah, I'm kind of curious about what sorts of other applications we might see people use this framework for, or even modifications to the framework itself. I can imagine that it could be extended in lots of different ways, because I know that the way you formalize this was this three-part loss function, right, that you had in terms of the network. So I can imagine there's maybe different ways to modify and make the constraint a little bit more complicated. I imagine that would probably, modify the training dynamics somewhat, but it does seem like something that could be extended in all sorts of different ways.
Yeah, I think so. I think it's a very general approach to using neural networks solving complicated optimization problems where it's not quite clear. I mean, it's usually a nonlinear optimization problem. It's not quite clear how you would go about that, but you kind of throw a neural network at that and see what the neural network can do. But also, you don't want the network to do some random things. You don't want to, let's say, optimize it to exploit certain things that are unrealistic. For example, in this case, making the face image weird. Because, I mean, the perfect way to hide gender information in an image would be just, just scrambling the image, right? Just replacing the image with pixels all of the same color or something like that, right? And so you have to kind of like add this little constraint that the images still have to be useful. And I think this could be applied to so many problems, in my opinion. I have not worked on any problems besides the biology and the biometrics in this case, but I can imagine there shouldn't be a restriction. I think that it should work for many different things.
Well, if anyone listening is interested, there's a wide open field here. So I'd love to spend some time on your educational work, and we can go on to talk about Lightning AI at the end. But first, as I mentioned at the beginning of this, I and probably many listeners have seen plenty of your educational content. What was it that inspired you to get into education in the first place?
Yeah, it's a good question. I never really, let's say, thought about what was the inspiration for that. It's just, I like it. It's fun. I enjoy it. It's like, it's the best thing in the world, to be honest, to write something and someone emails you, hey, this was super useful, helped me a lot in my job interview or my PhD defense. And it is awesome to do something where you feel like, okay, you did something useful for the world. You kind of contributed. What you do makes sense. It's useful, and you are helping people. I would say it's this feeling of I don't know, like doing something that other people enjoy. It's maybe I'm in the wrong business. Maybe I should be in entertainment, no, because that's a kind of same thing. People like maybe doing things that other people enjoy. There's something contagious about that. There's something about like this being really, I don't know, it makes you feel really like you do something useful. I don't know. That's maybe it, I guess. Maybe another aspect could be that it's also a good way to learn, in my opinion. It's like, I mean, there may be more efficient ways to learn, but if you write about something, you spend some extra time on making sure you understand it well. So if I write about confidence intervals, I do as much research as I can before to make sure I don't miss anything there. And I make extra sure that what I'm putting out there is correct. Maybe I would go beyond the time I would spend on it if it's just for my own curiosity, basically. So in that sense, it is a good method to teach yourself too, in a way. And what I really like is you get feedback from the community. So sometimes I put a blog post out there. I think it was, for example, true when I did, I mean, it's many cases like that. When I recently wrote an article about the data pipes, the new data pipes in PyTorch, or the M1 support, ARM support, the GPU support specifically in PyTorch. And I wrote these articles, there were always people from the community who pointed out things I didn't know about. So sometimes they find little issues here and there, but also like tips and tricks or something that goes beyond that you would know. Because in that case, one of the PyTorch engineers was reading that and said, for example, there's like a little caveat. You have to put in the data pipe example, the shuffle after the batching. Oh, no, it was the other way around. Something like that, where you had to be very careful where you place it. It was not very, it was nowhere written down. It was just a little caveat. And things like that, I wouldn't, find out by myself. It's in that way very productive. You do something, you feel like, oh, you understood everything. And then there's always someone who points out something you wouldn't otherwise learn by yourself. And this is like, I feel like that's what makes the community great. It's like the sum is bigger than its parts, where you have like experts in all different areas. For me, I would say I'm very broadly interested in very many different topics around, let's say, machine learning and deep learning and coding. However, I'm not super specialized, let's say, in engineering, or I'm not super specialized in a certain deep neural network architecture. And if I would write about it, I would put something together that is correct and worthwhile, but there will always be someone who knows a little bit more and would help me or give me feedback, which is then helping me getting a better understanding or learning something I wouldn't otherwise learn. And that is also very powerful and very motivating to me.
I think those are really interesting ways of putting it. And I think I found very much the same thing when I've been a teaching assistant, for instance. So I guess on the one hand, it's like I'm interested in this area. Presumably that has to do with why I might be interested in educating others about it. And so I can understand things better by explaining. But then, as you said, there is also just that joy of being able to see somebody's eyes light up when they understand something or come across a new concept. And I guess there's different ways it comes across, right? There's like the very immediate visceral feedback that you can get when you're teaching somebody one-to-one. But then also, I imagine for a lot of the content you produce, so some of your YouTube videos, maybe there's a more immediate feedback process, but I know that you've also written multiple books at this point, and I imagine that there's maybe a trade-off there, right? There's maybe a level of like scalability of, okay, well, I put this book out there and just a lot of people can read my book as opposed to, coming to an in-person lecture. But there's maybe a longer feedback process between my putting the content out there and then seeing how useful it is to people.
Yeah, that is an interesting way to put it. I must say, I like interacting with people in person. I'm just back from the SciPy conference from Austin, just came back 2 days ago. I was going through some canceled flights, but it was overall a very worthwhile experience. I like the interaction where I feel like it can be very powerful and very productive to interact with people, and attending things live and being able to ask questions. It's somehow different than, let's say, posting something online where you have this delay. And also there's only so much, let's say, you can put down as a response, and then days go by and then you get the response to the response and so forth. And if it's live, it's more interactive. There was just like I had a discussion with Thomas Fan from Scikit-Learn, where I was complaining about the limitation of the Scikit-Learn pipelines when you do, let's say, the permutation importance and you have categorical data, and so you have a one-hot encoding, but you don't want these variables after one-hot encoding considered as individual variables. You want to group them together. And I was complaining this is a little bit tricky to do in Scikit-Learn. And he showed me with a column transformer and using pandas in the categorical data type how you can hack something like that together in like 5 minutes. So we sat down, he opened the Jupyter notebook, and he had to like try it a few times, but then it eventually worked. And this is something I feel like is very powerful about in-person interaction. I was explaining what I wanted, and we were working together on this. And yeah, these interactions are very powerful. You don't really so easily have that online. However, another point you mentioned is the scalability. So I think for me, it's like I've been at the university for 4 or 5 years now, University of Wisconsin-Madison, where I've been teaching machine learning and deep learning classes. And I try to update my class every year. But there are still classes, let's say, where you can't you can't like totally change the content and make it, let's say, more advanced or more detailed, because every year students want to learn about the fundamental concepts, right? So you have to kind of stay at the fundamental level, which is very important and very powerful. But then sometimes, I feel like when you do this a couple of times, it could be more productive, let's say, to do it one time really well, record it, put it online where everyone can watch it, and then work on the next content, right? So working on a follow-up material, because a lot of people ask me about it, like, hey, I finished your course, what should I do next? And working on that next thing, I think that's also something I was thinking more about, which kind of led me to Lightning AI, essentially. So so in a sense, I think I wouldn't say one is necessarily better than the other, like in person versus recorded. However, there are certain, let's say, trade-offs with both formats, right? So, yeah.
Yeah, absolutely. Well, now that you've introduced the segue, let's close up and talk a little bit about Lightning AI. Can you tell me about what it is and what you've been doing there?
What I'm doing there is essentially education, also essentially creating educational material about machine learning and deep learning and helping people, to get into it and understand it, and basically producing content that helps people learn. But Lightning AI specifically is essentially something we launched just a few weeks ago. It's essentially a platform that also makes certain things easier. So Lightning AI is essentially a framework where it allows you to really put together components from the machine learning ecosystem to build a machine learning application. And this could be anything. I mean, really, it's very flexible. It can be a research demo. It could be a cluster scheduler. It could be an app where someone uploads X-rays. It could be, for example, a doctor who's using your app to, let's say, more faster diagnose whether there is a fracture in a bone fracture or something. I mean, of course, we don't want to replace doctors here or something. It's an example where someone would maybe develop an application when, let's say, there's no doctor available and you have something that, let's say, people can use to prioritize patients, for example, something like, I mean, you can basically build anything there. And the idea here is really to make that easy, because for me, a person coming from academia, what I usually ended up doing is I train my model, look at some results, look at the predictive accuracy, let's say, put it together in a table compared with other models, write my paper and be done with it. But then how do you really use that model? I mean, the gap between the machine learning research community and the, let's say, people who use machine learning in applications, production environments, and so forth. Nowadays, I would say it requires a team. So, I mean, I can remember when we did these semi-adversarial networks, we were invited to a conference and we were developing a demo. So back then, but I was actually 99% of this was my collaborator, Vahid, who developed a Flask app to basically have this model so that people can come up to the computer and see how it works with a camera and how it, let's say, modifies the face images and stuff. But this took a lot of work to just put a model into this interface so that it is actually an application, or a demo in this case. And how can you make this simpler and go to really production-grade applications? And so for this, it was also running on a laptop computer. So sometimes, maybe a laptop is enough. You can run things locally. Sometimes you need the infrastructure, having multiple GPUs, for example. And so Lightning is a framework that solves all of these problems. So you can develop a research demo where you have, for example, a Gradio or a Streamlit interface. You have something that runs your model. It trains it. Once it's trained, it's deployed into this interface. And then let's say it shuts down these GPUs because training is finished. You can have a cheaper GPU just for serving it, and you can share it with others. And making this really simple, like making this possible in days and not weeks, essentially. And on top of that, what one restriction is, I think, you can have a lot of cool apps and you can share them. But how would someone else build that? I mean, it is much easier than, let's say, using something else, like building it from scratch by using these pre-built components. However, it's still, I would say, a learning curve to come up with something like where you build like your X-ray classifier or something like that. So the idea is also that we have a gallery where people can put their apps on. It's not required, but you can make that public. You can put your app on there, and then people can clone it and then modify it. So instead of starting from scratch, you use a working app and make modifications. So maybe you don't need an X-ray classifier. Maybe you need something for I don't know, like identifying bird species or something like that. So you can just swap up the classifier. You don't have to re-engineer the whole thing, right? And this is also how I usually work. So when I do research, for every research project, I start with one of my previous projects, or also for teaching. I rarely would code something from scratch because you are duplicating efforts. You are really reinventing the wheel. And that's exactly what we are trying to avoid. We try to have this gallery of examples that people can reuse, clone, modify. And then what's really nice is you can run it on your computer. You can change one line of code. It runs on 1 GPU, 4 GPU, however many you need. And this whole thing is open source also, I should mention. The only thing is when you run it on the cloud, it's using the Lightning Cloud, where you have, let's say, you can have, if you run it on a CPU, it is free. But if you want to, let's say, have 4 GPUs, you have to pay a small hourly fee, of course, to rent these GPUs for the time you need it. But other than that, it's an open source framework. Everyone can contribute. You can share your components in your apps. You don't have to, but yeah, that's the whole idea behind it, making this whole process of taking a model and building an application easier.
That's very neat. And as you've already pointed out, this is solving a really important problem that I can see kind of everywhere. It's definitely a pretty big gap between, as you said, the research code that gets produced and then actually deploying it somewhere. And that requirement of manpower and time and just large teams and coordination to do that does make it really difficult, I think, to operationalize and really make ML systems as useful as they can be. So I am very excited to see more companies like Lightning that are pursuing this.
One little thing I wanted to say about that is also, you don't need to be a company to, let's say, take advantage of this to build your application faster with reducing your costs of getting to production. But also as a researcher, I think, and now it's 2022, we went through this phase where I remember when I started, it was cool when you uploaded your code on GitHub. You were like, okay, you are maybe in the top, let's say, 5% of people who make your code reproducible, and which was good for science to make this code available and reproducible. Nowadays, also many people or bigger companies, they write blog posts to make the research more understandable and more accessible, which I think is also important. But yeah, what is really the next thing of having your research more accessible or, let's say, relatable? It's, I think, really developing an application. If you have a conference paper, you get invited. Wouldn't it be great if you also have a demo where you can really showcase your research rather than showing a paper or a poster where everything is static? And I think Lightning AI also for researchers, even if you don't want to productionize your model, it's really nice to have this option where you can very easily make a working demo of your research to really, showcase it and have people interact with it, in my opinion.
Yeah. I do think that prospect of, something visual that people can really interact with is a fantastic way to get folks more engaged with what it is you're building. So to actually close out here, I'd like to end with maybe just one final question, which is a bit more broad than Lightning AI. As somebody who spends so much time in AI education yourself and, as an academic, if you could give just one piece of advice to other educators who are maybe not as far along the path as you are, what would you like to impart to them from your own experience?
I would say it's important to have a big picture of how different of the different topics, so you know how things connect. But like we talked about earlier, it's maybe not feasible to do everything in super much detailed manner. Like you don't have to understand maybe everything in detail. It would be good to understand the overall ideas of everything, but then maybe focusing on one thing and doing one thing well, than being all over the place. And this is also true for me. I always have to remind myself I can't do everything. Even there are so many interesting things I want to do, I have to scale back and say, okay, I can do this one thing or this handful of things very well. But if I want to do more, it would be at the cost of these things. So prioritizing and maybe being focused. I think focus is a good question, good advice, because otherwise you end up doing a little bit of everything, but nothing really well. And that is, I think it's not also getting you to the best potential and putting something useful out there. I think nowadays, so many people produce so much awesome content. If you want to, let's say, really contribute and do something that people find useful, it would be going into more detail in certain ways that is not, let's say, covered so far.
Yeah, absolutely. That makes sense. It's definitely a process of figuring out what is that kind of niche that can be offered.
Sorry, if I have one, now I have basically the thing I wanted to say is you really need to also find something you are excited about. I think if there is something you're excited about, you will automatically produce something great. I think if you picking a topic that is maybe hot and important, but you're not excited about, I don't think this will be something where you enjoy the work and produce something that's awesome. I think finding what you're excited about and focusing on that, I think that is my advice, maybe.
I think that's really vital. Yeah. So, for our listeners who might like to learn a little bit more about you and your work, where would you send them?
I would say my website and maybe Twitter. So on Twitter, I'm RASBT. So that's because I was back in the day trying to minimize the characters, the number of characters, because they went into your character limit. RA for the first initials of my last name, and then SBT just for Sebastian. So anyways, I'm very active on Twitter and on my website. SebastianRaschka.com. That's usually where I collect everything. It's my research, my open source projects, links to my courses, and things like that, links to talks, and so forth. Everything I do basically is on my website in some form, so that might be a good landing page if someone is interested. Also, my books, not the books themselves, because they were published with a publisher, so they wouldn't like if I would put the PDF up there, but at least links to the books. Yeah.
Lovely. Well, I'll include all of those links in the show notes. And thank you once again for coming to appear on the podcast today. It was wonderful speaking with you.
Yeah, thanks for the invitation. I really enjoyed this, and I will keep reading and listening to The Gradient, which is actually a great resource. And thanks so much for putting it out there, making it a resource freely available to others. It's awesome.
That's a wrap for this episode. Thank you so much for listening to this edition of the Gradient Podcast. You can find our podcasts, newsletter, and other articles from thegradient.pub and our Substack at thegradientpub.substack.com. If you liked the episode, please consider supporting us by sharing it with a friend or subscribing. And as always, we appreciate your ratings and feedback. See you in the next episode.